statement of Taylor's theorem. Let f of x be n plus 1 times differentiable on utilized b. Then for every x naught x interior of b that seizes the point C between x naught and x, such that f of x is equal to the Taylor polynomial over n x naught of f at the point x plus the derivative over the n plus 1 of f at c divided by n plus 1 factorial times x minus x naught to the power n plus 1. So here the Taylor polynomial t is defined as f of x naught plus f prime of x naught times x minus x naught plus fn of x naught divided by n factorial x minus x naught over n. So this is a statement, yeah.
What's after n plus 1, the first line?
Sorry, sorry.
What's after n plus 1 in the first line?
Times.
Oh,
So for example, the case n equals 0, what you're saying is that f of x is equal to f of x naught plus f prime c x minus x naught, right? Over some c between x and x naught. And this would be the inequality, right? Should recognize the inequality. So you have a differential function, and you find that f of x minus f of x naught divided by x minus x naught is equal to f prime at some intermediate point, right? So the mean value theorem is about approximating f of x with the zero order polynomial of f at x naught, which is just the constant f of x naught. At least it's a way of looking at it. And for n equal 1, Taylor's theorem gives you f of x equal to f of x naught plus f prime of x naught x minus x naught. So the first order Taylor polynomial is just the linear approximation of f at x naught plus, okay, the other term is the second derivative of f at this point c divided by 2, and then there is an x minus x naught squared. So this is the second order. So the case n equal 1 of Taylor's theorem is about the distance between f and its linear approximation, right? So this would be P1 x naught f at x, which is the linear or tangent line, linear approximation of f at x naught. And I mean, the more derivatives you have, the more you can say about this function. You can approximated with polynomials via an higher order. Okay? Now, so what is the proof? Okay, let me say that I don't know, x naught is less than x. I mean, otherwise we got an analogous argument. Okay? I'm still writing that. Thanks. So this is just a statement and two cases of the statement, okay, that are just users in.
This is an equality, right? It's not an approximation.
Well,
Like,
yeah, it's an identity. I mean, an approximation in the sense that if you want to see it as an approximation of f of x with the first two terms,
Mhm.
the linear part, right? And then there is an error.
That's the error? Okay.
Okay, which is really an error term in the sense that you don't know what c is, so it's not really explicit. It's just something you can be happy of estimating. So you can. So the moral is that you only estimate the size of this object, of this reminder here, because it involves a point c that you cannot explicitly characterize. So you cannot really say much about this point c. It will depend in a very implicit way from x naught and x and f and n. That's why it's called, I call it an approximation identity. It's something, some of the idea is that you have your function, you approximate it with a simple object, a polynomial, and it's an approximation in the sense that this quantity that's left out, it's really just something you can try to estimate. Okay? So, the proof. Let's focus, for example, on the case where x naught is less than x. So you have a and b. I mean, the proof is not different than in the other case. And now let me define, for a variable t between x naught and x, let me define a function, f of t, by setting, so let me just check the formula so we avoid writing. Okay, so this will just be f of x minus the Taylor polynomial of order n at the point t of f computed at x. So you compare f with all the Taylor polynomials, okay, that you obtain by moving the base point t. So you see here in the formula is the relation between f and the Taylor polynomial at x naught, okay? Now I'm constructing an auxiliary function f of t, which is the distance of f and the Taylor polynomial at the point t. What does it mean explicitly? This is f of x naught minus, so what is the Taylor polynomial at t? Is f of t plus f prime of t times x minus t, right? Plus, and then I go on, the derivative of order n computed at t divided by n factorial times x minus t to the power n.
do you mean f of x or f of x naught?
Oh yeah, this is f of x. When I write down this f of t, I'm really considering the distance of f from its best, from various Taylor polynomials, right? I'm just changing the base point t. So this is the point where I'm computing f and its derivative is up to order n. For each t, I have a polynomial, okay? And I'm checking these different polynomials, I'm checking their value at x, and I'm taking the difference. All right? So just to make an example, say that this is the point x, this is my function f of x. Okay? So if I take t here, this will be the linear approximation at t, right? This will be f of t plus f prime of t x minus t. At the point x, this takes this value, right? here would be f of t, right? It
Mm.
would be f of x minus linear approximation with base point t. If I do, instead of using t, I use this point s, this will be the linear approximation, f of s plus f prime of s times s x minus s. And then, in this case, this will be the value, right? So this thing here will be f of s. Alright? That's the meaning of that function. It's measuring at the point x how far the function f is from its linear approximation based on another point t. Okay? So you see, this function is somehow telling you how this is a picture in the case n equal to 0, right? My picture here is for the case n equals 0, where, so in the case n equals 0, sorry, n equals 1. N equals 1. In the case n equals 1, I am subtracting the first order Taylor-Ford number, right? Which is this guy. Okay? Then, I mean, the proof will actually work for the any kind of, any order, for Taylor approximations of any order. But for the purpose of drawing pictures, I think it's healthier to just stick to the near one, okay? But the argument is general. So what about this function f of t? Well, this function f of t, it has a very nice derivative, because if you take the derivative of this function, so you are differentiating it as a variable, right? So what is the derivative? What we get is, okay, f of x doesn't contribute to the derivative because it's constant, right? In t. To differentiate this in t is fine. Right? So this is a minus f prime of t. Okay. Then I have to differentiate this guy, right? And so maybe let me put the minus in front of this square bracket. There is the minus right in front of the square bracket, and then so I got f prime of t. Then I differentiate this guy. So here I have something like, when I first differentiate, I have the derivative of a product. So when I differentiate x minus t, I got the minus sign, right? So this gives me minus f prime of t. But then, which will cancel that. And then I differentiate f prime, and this gives me an f second, right? So I got plus f second of t times x minus t. Okay, so far I have differentiated the first term and the second term, right? So what would be the third term here? Something I didn't write down. This would be f second of t times x minus t squared over 2, right? The next term, if I have at least n equal to. Then when I differentiate this guy in t, when I first differentiate the polynomial part, I got the 2 coming down and cancelling with the 2. So you got an x minus t, so with a minus in front, because we are differentiating in t, right? So the derivative of this guy, when I differentiate the second factor, is minus f second of t times x minus t. And then the derivative falls on the second derivative, and I got a third derivative times x minus t squared. Okay, then I think you got the idea, right? You go on, you see, you go on, and each time you differentiate, and you cancel the previous term, and you create a new term that will cancel with the next guy, okay? So if you keep on doing this thing of alternating signs, in the end you differentiate the last term, right? And the last term will give you something like minus fn of t times x minus t to the n minus 1 over n minus 1 factorial plus fn plus 1 of t times x minus t n over n factorial. This is the derivative of the last term. right? If I take the last term and if differentiate it, when I differentiate this guy, I got an n coming down and giving me a 1 over n minus 1 factorial times x minus t to the n minus 1 with a minus in front because there was a minus t here. And then everything is multiplied by fnt. And then the derivative falls on fnt itself, and I got fn plus 1 of t times x minus t over n factorial. And now the game is that this guy, the guy with the negative sign, will actually match with something I was differentiating at the previous step. So all this thing, this whole piece here is equal to 0. Okay. So the bottom line is that if you define f of t as the difference between f of x and the Taylor polynomial of order n at the point t of f, definition here. So you see it's curious because the function is a function of the variable t, and f of x doesn't depend on t, and the Taylor polynomial at x doesn't depend on t here, but it depends on t as the base point. So you see the dependency on t better when you write down the full formula, right? And if you start computing the derivatives, you have this cancellation gain between one term and the other, and you're just left with the last term. So if you throw away all the zero part of it, you're just left with a minus in front, this last guy that didn't cancel with anyone. So if I define this thing like that, then f prime of t is equal to minus f n plus 1 t x minus t to the n over n factorial. Okay? That's can I erase this one? This bottom line? Okay, maybe I can, okay, let me first. Okay, so this is f of t. So now think about, okay, let me see if I can make this simpler than it is on the book. So what follows is an attempt. I'm not sure it's going to work, but it should. So let's see. What happens if we compute f at the point x? So if I plug in x equal to t. So what goes on, you see, is that if I plug x equal to t here, so I'm computing the Taylor polynomial based at the point x at the point x. So I'm taking this thing in square bracket and I'm plugging in t equal to x. What is that? This is f of x plus a bunch of zeros, right? So the value of the Taylor polynomial with base point x, the value at x of the Taylor polynomial with base point x is f of x. So if I compute this at this guy at t equal x, this will give me f of x, which I'm subtracting by f from f of x, right? So this is 0. So now f of x is equal to 0, right? What is f of x naught? F of x naught is equal to the left-hand side in Taylor's formula, right? It's going to be f of x naught is the difference of f of x with a Taylor polynomial with base point at x naught computed at x. So well, f of x naught is equal to this minus that. So remember that the goal of the theorem is showing that this thing is equal to fn plus 1 some point c times x minus x naught with n plus 1 divided by n plus 1 factorial. Okay, so the goal of the game is showing that this thing is equal to something. Alright? Now, okay, I see. Okay, this is instructive, so let's do it anyway. So what I'm going to do will not lead exactly to the statement of the theorem, okay, but very close. And then we will need to do a slight variation of what I'm going to say. So what happens if now I apply the mean value theorem to this function? So if you apply the mean value theorem to f of t for t in the interval x0 x, then you find the existence of a point C belonging to x0 x such that f of x minus f of x0, and this is good because that's the guy we want to compute, is equal to f prime of C times x minus x0. Right?
Mm-hmm.
So switching the terms, right, it's good to write this guy as, so f, this will be minus, so this is equal to the Taylor polynomial that we have two, something like, what is f prime of C? I have it over there, right? F prime of C is minus fn plus 1 computed at C over n plus 1 factorial, and then we sorry, over n factorial. And then I get this x minus t to the power n, right? So, and this will be x minus c to the power n, and then x minus x naught. So this is almost Taylor's theorem, right? Let me write again for you.
When you did f of x naught, like look at even the big f of x naught on top, should the why is the Taylor polynomial and that one not at x naught?
Because the definition is that f of t is f of x minus the Taylor polynomial based at t. So the t variable, so the variable of capital F is not this, it's here.
What does that mean in terms of the picture? Like,
But it's f of t is obtained, you move the point at which you compute the Taylor polynomial, and you check the difference between this Taylor polynomial and f at the point x. So it's like when I compute f of t, okay, I construct the Taylor polynomial based at t, which is the approximation of order n of your function at the point t. And then I check what the approximation based here does at the point x.
so in there you're changing where you construct the polynomial for, but not
Exactly.
the point that you're comparing.
Yeah, we are always comparing them at x.
Okay.
But then we are comparing, okay, yeah.
Should it be f of x instead of f of x naught?
What, sorry? Yeah, you're totally right. Here is f of x. Thank you.
Okay.
And I wrote it correctly over there. So that's just this is a field effect. So I'm not really proving the theorem. I'm kind of doing the natural thing. Because if I show you directly how you have to do it, it sounds a bit like unjustified. Okay, so I first want to show you why this thing here doesn't exactly work. Because if you do it, right, you apply the mean value theorem to this function, this would be the natural thing to do, you find this formula. So what is this formula? Let me write it down again up here. So okay, so what we found is this. So what we found is that what do I find from is that d is equal to the Taylor polynomial at x, but the other term is not exactly the form that we were expecting it to be, right? Because the error term now is something like what we wanted we didn't exactly prove the theorem yet, you see? So what we wanted was to show, to find the point C. So here we have there exists C between x naught and x, such that. And what we wanted was a point C between x naught and x. So the C appearing in this formula doesn't need to be the C appearing in the other one. Okay, they will be different points in general. But what we wanted was to express this remainder term in this form, right? And instead, we expressed it in a similar form, you see? It's quite similar. Still there is the n plus 1 derivative of f at some point, right? Still there is something that is kind of a power n plus 1. It's just that here you want it just in terms of x minus x naught, while over there you found it in terms of x minus c to the n and x minus x naught. So it's not exactly the right thing, okay? So how do you fix that? To fix that, you apply the mean value theorem not at f of t, but to a slightly modified function, which is the following. So the function that, so to fix this, you set g of t to be, so let me be sure that I get the right thing. So f of t minus x minus t over x minus x naught to the n plus 1 times f of x naught. Okay, so this is a bit mysterious, huh? It's okay. The point is that it is a bit mysterious, but it doesn't really change the substance of the argument. Okay? So the idea of the proof is really comparing your function with its Taylor polynomial at different points, okay, and then using the mean value theorem. Now, essentially, we are doing the same because f of t still is the comparison of f and its Taylor polynomial computed at x, right? And then you change the base point. But it's just, instead of using f of t and that's it, we are kind of adding a polynomial correction, x minus t to the n plus 1. This is just, is not changing the value at x. Actually, at x, the thing is still 0, right? Because you're adding 0. At x naught, you are changing the value at x naught because you're making now the function, the new function at x naught is equal to 0. And the thing is just is adjust exactly in a way such that if we apply the mean value theorem to this guy, we get this formula, which is what we wanted, instead of this formula, which was similar to what we wanted, but not quite the same. So it's one of these technical tweaks that, I don't know, I don't see a particular justification for this, a particular geometric intuition for this thing, okay? So while it's quite clear, I mean, I think that the geometric intuition behind this f of t is quite plain. You're just comparing your function and its Taylor approximation at different points. I mean, it's not maybe the first thing that will come up to your mind, but once you see it, it's okay, all right? And it's nice to see that it brings you almost at home, okay? It almost gives you the result. Actually, for all practical uses of Taylor's theorem, you could be good with this formula, okay? So for example, if you want to use this Taylor's theorem to justify the use of little o's in the computation of limits, this formula is as good as this other one. There is no substantial difference in working with this one or the other one. So the only reason why I am going to prove this one and give a name to this formula and not to this formula is that this one is more elegant, right?
Typical.
I mean, the remainder, you see, the remainder is expressed in the more compact form. It doesn't have this double product that looks a bit strange, would be harder to remind, I don't know. It's just a slightly more complicated formula, the first one, okay? So even if this is the one that has the more natural proof, okay, So the proof of this one will be less natural because it will involve the use of this function, which is, less intuitive, okay? We will prove this one because then the result is cleaner and neater. But somehow you see that there is really no big difference in the kind of argument you're going to do. Because now that I've shown you the right formula to use, what is the proof? It's just the same thing. You just apply the value theorem, okay? But to G instead of to F. Yeah.
For the first equation, is there a factorial under maybe the second term?
Yes, a factorial. Yeah, thank you. That's divided by N factorial. Okay, so what about this new? Okay, I have to be careful not to erase f prime of t because this is going to be needed. Okay, so what about this function g? Okay, this new function g, if I compute it at x, it is equal to f of x minus x minus x naught divided by x minus x naught n plus 1 f of x naught.
You mean g of x naught, right?
Now here I'm computing g of x.
Oh, wait.
So, okay, let me
What?
put this up here. That's something we already computed and it's going to be useful. Again.
Wait, how is
G of x should be 0. I mean f of x minus 0.
Ah, sorry, so that's, okay, yeah. That's what you got here, yeah, thank you. So, you see that, that's the efficient, it's x minus t. So, if I computed at x, I got f of x, which is 0, we already computed that. So this guy is 0, and this guy is separating 0. So, you got 0 minus 0. While g of x naught is equal to f of x naught minus x naught over x minus x naught n plus 1 f of x naught, and this is just f of x naught minus f of x naught again, right? So that's again 0. Yeah.
I see.
Should f prime be minus the n plus 1 derivative of t?
Yeah, thank you. This is just a formula we computed before, okay, so I was recording it because we need it now. So what is g prime of t? G prime of t is equal to f prime of t, which is written up there. So this is f n plus 1 computed at t divided by n factorial times x minus t to the n plus, so, and then I have to differentiate in t distinct, right? So I got an n plus 1 coming down. This leaves me with x minus t to the n. Then I have to differentiate t, so I got a minus here too. And then I have an x minus x naught to the n plus 1 f of x naught. So just take a second to double check the formula, right? I just did f prime of t so I just computed g prime of t. So I got, when I compute g prime, I have an f prime, which is what I have written here. The first term is f prime of t. And then there is minus the derivative of this thing, right? Ah, okay, but there is minus is a plus, okay. That's how it comes. Right? Okay, now to conclude the proof of the theorem, you just use Rolle's theorem, right? Which is a particular case of mean value. So all you say is that, well, g is equal to 0 at x and at x naught, right? So there exists an intermediate point where the derivative is equal to 0. So by these two things, there exists a point C between x naught and x, such that G prime of C is equal to 0. And what does it mean that G prime of C is equal to 0? It means 0 equal to minus Fn plus 1 at C divided by n factorial times x minus C to the n plus n plus 1 x minus C to the n over x minus x naught to the n plus 1 times f of x naught. Well, I'm just writing down this formula here. This is audible, I mean, it's not proof. That's a bad proof. It's not a nice proof. I mean, that's a stupid proof because you don't really see what you're doing and why. Okay? So you saw it with the function capital F of t, and it was leading to a result that actually for any practical purposes, it's as good as what we wanted to prove, okay? But now for some reason, the tradition is to prove Taylor's theorem with the remainder in this form. And so we have to resort to this more mysterious function G, which is just the point of G is that it has the algebraic structure that gives it a nicer result. But I really don't see, you see, I mean, I'm just playing a bit of algebraic chemistry with these formulas to find a nice formula that gives me the right thing. Because you see now how it combines nicely to give you the right result, right? You have that this is equal to 0, so you can cancel this x minus c. Actually, let me remind you that Rolles give me a point between x naught and x, right?
Mm-hmm.
So x minus c is different from 0. So I can cancel it from both sides of the thing, right? So the point c that you find will be different from x, which means that x minus c will be different from 0. So you can take it out from from the area. What you find if you do that is that f of x naught times n plus 1 over x minus x naught to the n plus 1 will be equal to fn plus 1 c divided by n factorial. And then if you play again with the thing, you find that f of x naught is equal to fn plus 1 computed at c divided by n plus 1 factorial times x minus x naught to the n plus 1. Okay? And this is the theorem because, as we computed 1 minute ago, what is f of x naught? F of x naught is exactly the left-hand side of Taylor's series. F of x minus the Taylor polynomial.
What happened to n plus 1?
So you see, it's good up to here, right?
Yeah.
Then you bring the n plus 1 here, n plus 1 times n factorial becomes n plus 1 factorial, the definition of factorial. X minus x naught to the n plus 1 comes upstairs, right?
Mm-hmm.
And gives us the thing. And then what was f of x naught? F of x naught was exactly f of x minus. So we have proved that fn plus 1 of c over n plus 1 factorial x minus x naught to the n plus 1. This is equal to f of x naught, but f of x naught, it's written over there, is just f of x minus the Taylor polynomial centered at x naught of f computed at the point x. Right? So this is what f of x naught is.
Mm.
And that's Taylor's formula. Okay? So again, this is just life. Okay? I mean, if you want the elegant theorem, in this case you have to get it, but at the price of a stranger proof, in a sense. But all it's happening is really that you are tweaking a bit with the algebra of computing derivatives, okay, with the calculus side of this thing, in order to end up with a nicer form. Okay? Good. So that's the proof of Taylor's theorem. Now, so but you see, the proof doesn't really introduce new ideas or methods. I mean, it's just applying the mean value theorem to a suitably chosen function that takes into account the distance of f from its Taylor polynomial. Now, let me show you something that you know well. So we have seen that a necessary condition for having an interior extreme point is that the derivative is 0, right? But then you also know that you have sufficient conditions. So for example, if you have that the first derivative is 0, but the second derivative is positive, then you are at a relative mean, right? And if you know that the first derivative is 0 and the second derivative is negative, then you are at a relative maximum point. So you should be familiar with these statements. How do you prove them? You prove them by using Taylor's formula. Okay, that's how it goes. So let's see the statement. So theorem. So let f of x be say 3 times. No, it's just enough 2 times. Yeah, 2 times differentiable on an interval AB with f second of x continuous on AB. So you need the second derivative to be not only to exist but to be continuous. Okay? Then if x naught is an interior point to AB with f prime of x naught equals to 0 and f second of x naught positive, then x naught is a relative minimum point. What does it mean? It means that so that is there exists a positive number delta such that f of x is greater or equal than f of x naught for every x belonging to the interval x naught minus delta x naught plus delta. So notice that I require f second to be strictly positive. Okay. If f second is just non-negative, I cannot infer anything. Right? F second and negative is not enough. Take for example f of x equal to x cubed, right? Then f prime of 0 is equal to 0 and f second of 0 is also equal to 0. So in particular it is non-negative, right? But 0 is not a relative mean. So you really need in this theorem f second of x naught to be strictly positive. And you're going to see that very well from the proof, okay? So the proof will show clearly that we need that. Yeah?
So x naught, is it strictly a relative minimum or can it also be an absolute minimum?
Well, it could be the absolute minimum, of course. You don't know. Right? I mean, if you have a function that has so our function will be continuous on AB in particular, right? So it will have an absolute minimum on AB. But this absolute minimum may be achieved at the extreme points. So for example, the situation where this theorem applies, function that would be what we're talking about would be something like that, right? And in this case, I'm talking about this point x naught, which will just be a relative minimum. The absolute minimum will be achieved at A, and at the boundary point, being a minimum just means that you have right negative positive, no negatives. So that's all we can see, right? Okay, so let's prove this theorem, okay? So the first thing we have to do is showing that, so we make use of our assumptions of continuity, and we make use of the fact that, so since f second at x naught is positive, and f second of x is continuous on AB, there exists some positive number delta such that f second of x, or maybe, yeah, f second of z, let me call it, is larger than f second of x naught over 2 whenever the point z lies in x naught minus delta, x naught plus delta, right? So all I'm saying is that if I have a continuous function that takes a positive value, this would be f second at the point x naught, then there is a neighborhood of the point of the limit point x naught such that my function is above half that positive lower bound. So here you just use the definition of limit. So here I'm using f second of x naught equal to the limit as z goes to x naught of f second of z with epsilon equal to f second of x naught over 2. Right? And then I use the lower bound in the definition of limit. So the definition of limit tells me that for this epsilon there exists a delta, okay, such that f second of z is epsilon close to f second of x naught, provided x naught minus z is less than delta. So and if epsilon close to f second of x naught for this epsilon means in particular larger than f second of x naught over 2, larger than this guy minus alpha. So here I'm using, here essentially this guy is f second of x naught, which is the limit value, minus f second of x naught over 2. Okay, is that clear? Is it clear how am I using the definition of limit or not? Please say no if it is not clear, then I can explain. It's a big deal. For me it's not a big deal explaining this. Do you see the point? So if I pick epsilon, f second of z will be larger than its limit value minus epsilon, provided z minus x naught is less than that. And if I choose epsilon, this guy, I got the limit minus epsilon, which is, in this case, epsilon, okay, because the way of choosing this epsilon. Okay, so now apply Taylor with n equal to 1 to find a point C between well no okay, let me say this again. So fix now, okay, so fix x inside the interval x naught minus delta, x naught plus delta. Okay? Apply Taylor theorem to x naught and x, to x naught and x. Find C between x naught and x such that f at x will be equal to the Taylor polynomial of order 1, which is just f of x naught plus f prime of x naught times x minus x naught plus f second at c over 2 times x minus x naught squared, right? Right, I have presented, do you agree with that? Okay. Now, the point C, so think a moment about the picture. Here there is x naught, here there is x naught plus delta, here there is x naught minus delta. Here I'm just picking any point x between x naught minus delta and x naught plus delta. And then I find the point C in between x naught and x, right? In particular, the point C will also be inside x naught minus delta, x naught plus delta. Okay? So C belongs to x naught minus delta, x naught plus delta. We have that f second computed at C is at least f second of x naught over 2, right? That's how, what you guarantee for every point at Z between x naught minus delta and x naught plus delta. The derivative, the second derivative of f there is larger than f second of x naught over 2. Right? That's how delta came into existence in this proof. So delta came into play to tell you that every point at Z between x naught minus delta and x naught plus delta, f second is at least delta. Right? That's how delta comes into play into this proof. Now once you have this delta, you say, well, let me pick any point x in this interval. So in all this interval, f second is at least f second of x naught over 2. Okay? Then I pick any x. Apply Taylor to find the C, such that this formula holds true. Here, if an f second of C appears, and I'm noticing just that this f second of C is at least f second of x naught over 2. Right? Got it? Good. So, at the same time, f prime of x naught is equal to 0 by assumption, right? You agree? That's what we knew about f prime of x naught, right? That's so. When I take the conclusion of Taylor's theorem, this implies that f of x is equal to f of x naught plus, well, the term with f prime of x naught is 0, right? I don't need to write it down. It just appear because f prime of x naught is equal to 0. Then I just skip to the second order term where I have this f second of C over 2 times x minus x naught squared. And now I use the remark that f second of C is at least f second of x naught over 2. So I got an f second of x naught over 4 times x minus x naught squared. Okay? And what about this guy? Well, f second of x naught is positive, right? So x minus x naught squared, it's positive 2, if x is different from x naught. Otherwise it's 0. Okay. If I want to compare f of x naught with f of x naught, I don't need it here, right? So let us directly consider the case that x is different from x naught. So this thing here is strictly positive if x is not x naught. So if x is not x naught, f of x is strictly larger than f of x naught. And this proves that x naught is a relative minimum, actually a strict relative minimum. okay? In the sense that there exists a delta such that f of x is larger than f of x naught for every point which is delta close, with strict inequality if we avoid the trivial case. So if you want to change the conclusion of the theorem, you can have a stronger conclusion, okay? Actually, you have a stronger conclusion. Yes?
Can you just go over the last couple steps here, please?
Yeah.
The,
So here the first inequality is clear, right? I mean,
Right,
just,
yeah.
it's just Taylor's formula with n equal 1 using the fact that the first derivative is zero. Then I say, well, f second of c, it's larger than f second of x naught over 2, right? Because c, also c lies in this interval. So you see here, x minus x naught squared is not negative. So I can, if I change this with that, it goes, the inequality just goes down. Right? There's a positive number times a positive number. Here you have the same positive number times a smaller positive number.
got it, okay.
Okay, so this guy is larger than this guy. And this guy is strictly positive. Yes. So actually you can change the conclusion of the theorem if you want. It's actually stronger than, okay? So actually this is the theorem telling you that you have a strict minimum point. Relative minimum point which is strict. Okay? Yeah.
For the theorem to work, you need to assume f prime of x naught is 0.
Yeah, because if f prime of x naught is not 0, you cannot expect to have a minimum, right? Or a maximum. Because Fermat theorem will tell you that if you have a minimum or a maximum, an interior one, there the derivative is going to be equal to 0, right? So there is really no hope of doing that without that. So that's a necessary. So somehow, this is a necessary condition for being a relative minimum. And now I'm telling you, if you add to the stack of assumptions this one too, then combined you get a sufficient condition. Okay? Do you have other questions on this one? Okay, so let me just, well, of course you have an analogous theorem for a relative maxima. Okay, you just take f second negative, okay? And if you take f second negative in this proof, there's not so much change. F second of c will be uniformly negative. So here you got that this is less or equal than this minus f second, or actually plus f second of x naught, some negative number. So we just deduce that f of x is strictly less than f of x naught nearby. But somehow the proof is easier to tell with f second of x naught positive because it's easier to follow the inequalities. Okay, so that's why I've just used that case. That's exactly the same. So we just show you something else you can check from the Ring-Badu theorem. So take a function f of x defined on an interval AB. Definition: f of x is convex on AB if f of tx plus 1 minus t y is strictly less than t f of x plus 1 minus t f of y for every x and y in AB, for every t in 0, 1. Okay, so that's probably not the definition of convexity you're used to see, okay? You're used to see the one with the derivative, right? So you lie above your tangent line. That's the definition of convexity. And that was also in the homework. So, but what is, first of all, what is the geometric meaning of this definition of convexity? So I am taking an interval AB, right? I'm taking any 2 points x and y inside my interval. And then I'm taking what is called a convex combination of x and y. So when you do tx plus 1 minus ty for t between 0 and 1, this is called a convex combination of x and y. Why the name? Because you see, if you take this formula here, so what is that? This, another way of writing is, this is y plus t x minus y, right? If you want. So for t equal to 0, you got y. For t equal to 1, you got x. Right? So this thing at t equal to 0, so this is equal to y if t is equal to 0, x if t is equal to 1, and otherwise you see it's some intermediate point, right? So it's like as t goes from 0 to 1, I move along this segment, right? So for example, when t is equal to 1/2, I got x plus y over 2, which is the middle point, right? You see? So this is, for example, this would be x plus y over 2, which corresponds to t equal to 1/2. So the convex combination is just, and as t goes from 0 to 1, you just got the generic intermediate point between x and y. That's what the convex combination is, okay? Yeah.
If we like want to show that in our homework, do we have to prove it, or can we just like say?
No, these are related to the homework. In the homework, you have a definition of convexity. That's the one you use in that homework. Okay?
Oh, we can't use this one?
No, this is nothing to. No. Okay, with this definition, proving, for example, the first problem would be 1 second, right?
Wait, sorry, what did you say? Oh, gotcha.
It would be
Okay.
super easy, right? Because the first problem we want to check that if at the boundary point you're at 0, then the function is negative. And this would be weird because if f of a and f of b is equal to 0, this right hand side is equal to 0, and so f is negative at an intermediate point.
Yeah.
So with this definition of convexity, the first problem in the homework is immediate.
Mm-hmm.
Okay, but I want you to prove that starting from the definition of convexity that says you lie above your tangent line.
Okay.
Okay. Now I just wanted to introduce you to this definition. That's somehow the mathematically correct definition. Why? Why mathematicians? Okay. So first of all, but what the definition says. So that's just the convex combination of 2 points x and y, right? Okay. So what I'm saying here essentially is that take any 2 points, take the convex combination, and look at the value of your function at the convex combination, right? So let me draw a convex function. So I'm computing the value of my guy here, say at the convex combination 1/2. Okay? And then here you see I have the convex combination of the values of f at x and at y. So here I'm combining the base point, x and y. And here I'm taking the same convex combination, 1/3 of x, 2/3 of y, okay, or 1/2 of x and 1/2 of y. Here I do 1/2 of f of x and 1/2 of f of y. See? So if this is f of x, okay, let me draw a different function so the picture is nicer. And this is, I don't know, f of y. This point here, this will be t f of x plus 1 minus t f of y. So what this definition means is that when you have a convex function, you fix 2 points in x and y, and you compute your convex function as some convex combination of them, then the value of f at the convex combination is less than the convex combination of the values of f at the extreme points. So this guy at the bottom will be f of tx plus 1 minus ty, right? That's the value you pick at the bottom point. The value up here is the convex combination of f of x. So this is f of x, right? And this is f of y. And the convex combination of the two, you can compute it just by taking the line passing through and computing it here. That's the geometry of this thing. All right? So that's the real definition of convexity. And why people prefers this definition? Because it doesn't require derivatives, right? So the definition I put in the homework starts, let f be a differentiable function. Then this function is convex if you are above the tangent line. But the definition that is in the homework requires a derivative to exist. Okay? This definition, there is no derivative on the blackboard, right? I'm just using the function f, period. I just have a function and I can, and this is important, right? Okay, let's make a stupid example. So if you take the absolute value of x, do you think this has the right of being considered the convex function or not? Yes, it should be a convex function, right? But if I use the definition in the homework, I cannot even start asking the question because it's not differentiable at the origin. But this seems stupid. I mean, somehow, this object is convex. I mean, it's clearly a convex function, right? Actually, it's the limit of very nice convex functions. So if you just smooth it up the tip a bit, right? You can construct smooth convex functions in the sense of the definition of the homework that are arbitrarily close to that guy. So instead, you definitely want this to be a convex function, okay? But you gave a definition that requires the existence of the derivative, and so you cannot even say that. How stupid that is. Okay, you don't want to do that. But this definition totally makes sense. I just require here to be able to compute my function points, which I mean it's the minimum requirement to speak of a function. Okay? You can compute it. So you can compute your function, you can check if it's convex or not. Okay? More seriously, it's not that people is scratching their heads how to say that the absolute value is convex or not. The point is that this idea of convexity is important for functions not just defined on the real line, not just defined on R2, the plane, or the physical space R3. This definition of convexity is important because it's the definition of convexity you use for functions defined on infinite dimensional spaces. And that's what you're interested when you do evolutionary problems, when you do dynamical problems, okay? So when you do dynamical problems, you have a physical system, right? And you have your system starting from some state. Maybe because it starts from a state which is just a strange state because you perturb it, okay? So you have a room where the temperature is constant, and then somebody starts a fire, okay? So there will be a heat source, and the heat will propagate around the room, right? So now the system, what is going to do this system? Is going to, physics tells us that there is an energy of the system that you want to be minimized, right? Equilibrium is energy minimization, that's what physics says. But how do you get to equilibrium? So if you observe something that where nothing has happened for a sufficiently long time, you should observe an equilibrium, right? But how do you get from from a state where something happened to equilibrium? And the idea is that you get there by following the slope of an energy. So the idea is that here there are the states, the physical states of your system, and here there is an energy. Okay? So for every state of the system, I can compute a number, the energy, which would be typically the kinetic energy plus the potential energy. Now, what happens at the level of dynamics is that if you have a system at equilibrium, say it's here and it's happy to be there, okay? You perturb it a bit because you start a fire in your room. So you increase the energy of the system that now wants to go back to its minimal energy. So what you do from the mathematical and the physical point of view to describe what happens, you write a partial differential equation or an ordinary differential equation where you say the rate of change in time goes in the direction where the energy decreases. Does it make sense to you? Right? I mean, the system wants to decrease the total energy. So it will move towards the states of less energy. So if it starts here, it will try to go there. If it starts in this well, it will try to go to the minimum energy, okay? But you see, this game can be very complicated, right? Because if the system starts here, where does it want to go? Exactly, you don't really know, right? So, well, an assumption that it really simplifies a lot the analysis of these problems, and that luckily it's verified in a lot of cases, is when the energy is convex. When an energy is convex, there is not so much places to go. Even if the energy is not differentiable, if you have a convex energy, wherever you start from, you're flowing through to the global mean. Okay? And that's exactly the definition of convexity. If you take two states and you compute the energy of an intermediate state, the energy of the intermediate state is less than the convex combination of the energies of the two states. So that's exactly the kind of assumption that makes this kind of dynamical analysis possible in a lot of cases. Okay? So this is not strictly related to real analysis, but just to tell you where these things sits, okay, and where they go somehow in the real line. Yeah.
That's able to solve the problem of which direction energy wants to go.
Well, when you're convex, it's easy, right? Because when you're convex,
Right.
it's like you only have one, and at each time you always have a clear direction where you want to go.
But that function you drew is not convex,
The one up here,
not strictly.
yeah, this one here, that's not convex and it's more complicated. So when you are in this kind of situation, life is more complicated.
Okay.
Okay, so that's it. Next time I think we start talking about